I believe we ended with the quiz specifically. Questions 1 and 2 should be relatively straightforward because what you're doing is identifying the primary intermolecular force. Once you know the primary intermolecular force, you can rank those forces and decide which one's the strongest. That one's going to be the highest melting point. So if we went through real quickly and looked at these are all nonpolar covalent bonds, which is going to get us LDF forces. We have that OH, which as much as I hate doing it, we could immediately jump on that and call that hydrogen bonding. The next one's going to get us dipole-dipole. And remember, there were 4 forces, 4 structures. Listed 3 of them without repeating, which probably means that last one is supposed to be ionic. This does trip people up, and admittedly I should fix it so that it's a little bit more obvious. How do we know that one's ionic? Because there's a charge. Ionic compounds are typically metal and nonmetal, not always. We can sometimes hide it in charges. Okay? So, to a first approximation, the ionic is the highest or the strongest force, which is going to make it the highest melting point. So we'd go 4, 2, 3, 1. Okay? For the liquids, we'd go through and do something similarly. Dipole-dipole, hydrogen bonding, B, hydrogen bonding, LDF. Anybody see a problem? 2 of them have the same force, which means ignore it. Now evaluate. C has dipole-dipole as a second level. B has LDF. What does that mean? C is stronger. We'd get C, B, A, D. C bad. Follow? Cool. Last part, matching pairs that are most likely to form homogeneous solutions. Good thing I just deleted all of the forces because that's what we should use to answer the question. Okay. A has a dipole-dipole. Which of our solids is dipole-dipole? 3. So 3 and A are probably a good match. Okay. D was LDF. 1 was LDF. So 1 and D are a good match. Between B and C and 2 and 4, we now kind of come up with a dilemma. Okay. What is similar to ionic? Which of these is most similar to ionic? Hydrogen bonding or hydrogen bonding? You said the same thing, Mike. That makes no difference. Which of those is a stronger hydrogen bonding interaction? C. Which means the best solvent for 4 would be C. It's got the stronger interaction on that list. It may not work, okay, but that's irrelevant. It's the best given here. Does that make sense? Okay. If we wanted to then just do process of elimination and say I just wanted 1-for-1 matches, we could say B matched to 2. Okay. I could have also just said C and 2 work just as well. Okay. All of that would have been fine. Does that make sense? Do you get the idea behind those parallels and connections? Okay. So, why do we do this? Okay, so we've got some new information up here on the board. We've got 2 reactions, which we will discuss later in the semester. Let's take a look at this top reaction. Okay. These are mechanistic steps, by the way, so a little more context here. Mechanistic steps. What is a mechanistic step? You're like, I don't know. I didn't take second semester general chemistry. Oh, wait. You did. A mechanistic step is the simplest step for an individual reaction, okay, breaking it all the way down. Okay? So for this top reaction to happen, what I'm saying is that everything that changes happens all at once. I break the bond to iodine, and I make the bond to chlorine all at the exact same instant. That's how this happens. So I look beginning to end and see what changes happen. What happened in the bottom one? I broke the bond to iodine. Did I do anything with the chlorine? No, why is it there? Because if we continue to run the reaction, guess what the chlorine does?
Takes it away from the iodide.
It'll bond to the chlorine, or to where the iodide was. Okay? Not shown. Why would we think that would happen?
Positive charge.
A positive charge and a negative charge. All we're doing is bringing positives and negatives near each other. Both of these are different types of ways to do the exact same reaction, a substitution reaction, but there's different mechanisms behind how they function. Okay? To get these reactions to happen, they need to be put in an environment where these pieces can interact. What would that environment be? It's a hint, it begins with an S.
Solution.
Solution is a good option for it. Solution would mean everything's all together. The piece that I'm adding to cause these things to react would be the solvent. So the solvent is going to either potentially help or hurt each of those mechanisms, depending on how the solvent interacts. Kind of makes sense? The first role of the solvent is to do what? Dissolve. What does it mean to dissolve?
Break apart.
Break everything apart. Okay? Well, since we don't have really any ionic shown bonds, there's nothing to really break apart. So these are just going to be dissolved. Okay? Would I expect the chloride to dissolve in a nonpolar solvent? Why not? What force would a nonpolar solvent give me? London dispersion. What force is a chloride ion going to give me? Ionic. So for this top reaction, is using a nonpolar solvent a good idea? No. Because the very first rule that I wanted my solvent to do, to dissolve everything, it ain't going to do it. So I would need some level of polar solvent to help to dissolve it. If it wasn't polar, it can't dissolve this. Okay, well, which polar solvent do I want? Protic or aprotic? What's the difference? With a proton or without a proton? What was a proton? Keep going. Keep going. Positive. It's a positive. Okay, you're like, why are you like cursing me? It's a positive. So the protic has a very high positive. The aprotic doesn't. What is that very high positive going to try and do? It's going to associate with a negative charge. Is there a negative charge in this reaction? The chloride ion. So if I use a protic solvent, that positive charge is going to zero in on that negative and it's going to make it neutral. If it's neutral, can it react as easily? Protic solvents are going to suck for this reaction. The nonpolar doesn't get them to mix. The protic destroys the reaction and prevents it from happening. I only have 3 solvent choices. If the 2 on the outside don't work, we need to go polar aprotic. Some people laughed at the finger joke, whatever. Okay? We would have to hit the middle. So by looking at the dynamics of the reaction and thinking about these intermolecular forces, we can predict what solvents are going to help particular reaction mechanisms to occur. We could do the exact same thing with the bottom one. We're not going to, because we're not going to right now. We will do that when we talk about that reaction in Chapter 7 after spring break. Okay? So, solubility, could we get really tricky? Yes. Do these things dissolve in water? So what's the first trick? I'm going to argue that's not a trick, because in theory, everybody at this point can identify intermolecular forces, right? You can identify intermolecular forces when you're looking at a structure. What's the first trick? You weren't given structures. So what's the first thing you have to do? Draw the structure based off of the name, which means you have to know nomenclature. Okay? So we can embed tricky things behind this. Okay? Because you've all been actively working on nomenclature, you probably haven't, that's okay. We can race to see who gets there first. And I have this itching, sneaking feeling that I actually already drew these structures, and I'm drawing them all out unnecessarily. But we're just going to do it anyway. Okay? For the first exam, do I expect you to be able to name all of these? No. Really, the only one for the first exam that is borderline is chloroform. And the reason why you aren't really necessary to know that one is chloroform is a common name, not IUPAC. You're responsible for IUPAC. Okay? Yes?
What would that be called? Chloromethane?
Yep, exactly right. Chloromethane would be your IUPAC name. Okay, one carbon, so meth, all single bonds, or it's hybridization, better applied, but we haven't talked about that yet. So methane, and then the chlorine comes in as a substituent on it, so we get chloromethane. Okay? Why do we call it chloroform? Because somebody called it chloroform to begin with, and that jackhole had enough power that made everybody else do it too. Welcome to science. Okay? We also now have water, which I didn't draw up there, but there's our water. So cool, we could now identify intermolecular forces, which you can all now do in your head. Should water dissolve ethanol?
Yes.
Yes. Should it dissolve chloroform?
Yes.
Why?
Because it's a polar bond between carbon and chlorine.
Guess what?
No.
Doesn't do a really good job of it.
Okay.
Okay? So we can say, well, it's tetrahedral. Tetrahedral saying the polar bonds cancel each other. Polar bond 1 and none of the other ones are nonpolar. So that doesn't work out very well. So why does that not dissolve in water? This is a dipole-dipole. That dipole-dipole is a weak enough dipole-dipole that it can't interact with the stronger hydrogen bonding. Remember, sliding scales. These are not absolute comparisons. Okay? Next one, acetone. You say no. Why not? Same reason as chloroform. There's the dipole-dipole, but not going to happen. Guess what? It does happen. Those are perfectly miscible with each other, like infinitely. They do mix. Okay? Why? The difference between carbon and oxygen is larger than the difference between carbon and chlorine. That makes that dipole a little bit stronger. Add to that the bond structure around this, that shape, helps throw that oxygen out there to make it easier to get access to dissolve. Cool. Last one.
No.
It's got the oxygen carbon. Oxygen carbon, shouldn't it be soluble?
No.
No. Why not?
Space and the...
Okay. What can each of those bonds do? That's a hard question before you start getting too excited about it. Each of those bonds can do something fancy.
Rotate.
They can freely rotate. Sorry. They could freely rotate. So we could potentially organize this. So we were here and say, well, couldn't water interact? That's a sloppy way of saying water's coming in over there. Okay, couldn't it interact there? Well, yes, but this bond can freely rotate. In the process of it rotating, what could it do? It could fling this carbon-hydrogen thing where? Get the hell out of there, water. And what happens? We can't get that interaction. Okay? So when we're looking at these, it's not just the same force, but it's how similar are those forces, and are there secondary structural effects that could come in and entirely mess with the whole system. Okay? It's not as easy as it looks. Okay? Where you get tested on is largely, at least in multiple choice, the easy explanations. Where I could push you on is I could say diethyl ether. Let's just clean all that out. Diethyl ether does not dissolve in water. Like, well, you just told me that. Yes, I did. But now I'm writing it in a question. Diethyl ether does not dissolve in water, but tetrahydrofuran does. What was tetrahydrofuran? That's me being a jerk again. I apologize. Tetrahydrofuran does. What is the difference between those two structures?
There's no rotation. That's a fixed structure.
In the tetrahydrofuran, can we get that sigma bond rotation? No, which means we lose the ability to smack water molecules away, which means I do get an interaction between tetrahydrofuran and water. It does dissolve. Okay? So the question would be, explain that difference. Why does one dissolve and one does not? That is a perfectly legitimate test question. You didn't have to memorize anything, but you do have to recognize why these things are functioning. That is a much harder question, and that's not one I can ask as a multiple choice. Right? Kind of, sort of. I got a kind of, sort of, and a question. What do you got?
Is that steric interference when it's spinning around?
I don't even want to use the word steric or, yeah.
What portion is
Yeah.
strained?
I don't like using those words because I can't keep them straight. Okay. We will see those probably next week. But yeah, I have a hard time tracking those. Okay. So, what could we do with these interactions? Okay. A lot of you are moving into medical fields. You have to take biochemistry, and you talk to a biochemist, and you say, well, how much organic chemistry is in biochemistry? And they go, well, there's none. God, organic chemistry was the hardest class ever. Literally, the entire course of biochemistry is organic chemistry. There is no aspect of the course of biochemistry that is not OChem. Right? But how is biochem most easily taught? A memorization of facts. If you memorize the facts, you don't have to understand the underlying principles. Where are those underlying principles? Organic chemistry. So you will find lots of biologists and biochemists ignoring organic chemistry or failing miserably at it, but then doing very well in later fields because they can get away without having to understand the fundamentals. Okay? It does depend on the biochemistry instructor. Okay? One of my other colleagues here is the other guy that would teach biochemistry, and he equally agrees with me in the response that people have about biochem. It is an organic chemistry class, it's just applied. Right? So everything that we do with interactions, how a molecule interacts with another one, is organic chemistry. That is intermolecular forces. That's what makes up biochem. Right? Why does soap dissolve dirt? Why do we use dirt? Or why do we use soap? Right? Well, dirt and grease molecules are highly nonpolar. What would happen if I got nonpolar substances on my hand and tried to just use water?
Gonna get off.
The water just runs right off your hand. You can't get rid of it. So what do? You throw soap on it. What is the soap? Well, let's see. I think I got a picture. Sort of. So if we look at kind of a biochemistry type depiction of this, my major was biochemistry for the record, so I know a little bit about it. I'm allowed to make fun of it. That's my story. I'm sticking to it. Okay. If we look at a depiction of this, this is not an attempt to draw reproductive objects. We have a polar head, which interacts with water. And we have a nonpolar tail, which interacts with the dirt or grease. So this molecule bridges the gap between those two solvent systems, if you will, allowing them to mix. Okay? Officially, what happens is we build these things called micelles, where all the dirt and grease get trapped in the middle, and we've got this big old polar section on the outside, which dissolves in water. So we can then wash away the dirt and grease in these tiny little balls. Okay? And for those of you saying, well, biology doesn't need that, make it bigger, and you have a liposome, or whatever you want to call it. I don't know. You also have a bilayer sheet. You mean like a cell membrane? OChem. That's why it exists. Okay? We can memorize facts about those so that we don't have to think about the process behind it. And also for the record, That is okay. I may disagree with it, but that is okay, particularly with a class like OChem. You have an understanding and you have memorization of facts. If you just try to understand all the principles, guess what happens?
Fail.
You fail. Why?
There's too many.
You run out of time. Okay, particularly on a test. You can't apply all of those principles out. You have to have some facts memorized. If you just memorize facts, you do really well with exam 1, and then you progressively get worse and worse and worse throughout the year of OChem because you're now having to memorize more and more facts. You need a balance of both to be able to get through. Okay? So that's why we go through and look at some of those fundamentals and we try and scale those up. Kind of make sense? Chapter 2. Which moves us into chapter 3. Electrons exist in orbitals, and we have s and we have p orbitals. Okay? Officially, those are s and p. What kind of orbitals? Atomic orbitals. What happens if we make a molecule? Do we have atomic orbitals anymore?
No.
No, we have molecular orbitals. Everything must change. Okay? So ideally, you've had some time to go through and watch the video on molecular orbitals and understand why we need to bring them in. Right? Because now what we want to do is talk about how we can use those. Right? So our quick and, well, let's try it this way. How comfortable are you with hybridization theory? Like 2 thumbs up. The rest of you are like, yeah, that sucks. Cool. Okay? The way a lot of people think about hybridization theory is it's a giant black box, okay, with some magic voodoo stuff happening in it. Guess what it is? A giant black box with some magic voodoo stuff happening in it. It is literally that. We take our atomic theory, say for carbon, okay, and if I now make it methane, what happens? Well, I could draw out a Lewis structure for methane. I would need 4 molecular orbitals, okay, to run this appropriately. Okay. If we go back and look at carbon, well, it has 4 orbitals. So it should just work. What is the problem with those orbitals?
They're in the wrong orientations.
What is the bond angle between a px and a py? It's the angle between an x and a y axis, 90 degrees. What's the angle between our bonds and methane? Not 90. They're all equivalent. Are all 4 of those orbitals equivalent?
Yeah.
No. Which means something has to happen to those atomic orbitals. So this is hybridization theory. I don't know what happens, but I know it has to happen. Right? Orbitals sort of are matter, which means when we go through and do hybridization, I can't create or destroy them. So I can't just create a new orbital to explain molecular orbitals. I have to have some type of orbital to build with. Well, conveniently I do. What orbitals do I use for carbon?
The ones you got, your atomic orbitals.
Okay. How many atomic orbitals are there for carbon? And this is where you're like, I don't want to answer because this is a freaking trick question. Yes, it is a trick question.
5.
There are 5. What? Didn't you only draw 4? Yes, I did.
You didn't draw 1s.
I didn't draw the 1s orbital. Why not?
It's not a valence.
Okay. We're deciding to ignore the core. That the valence shell is the most likely thing to contribute to bonding, so I'm going to ignore the core. Okay? So there are 4 atomic orbitals for me to work with in this theory. Okay? Of those, which should I use? Well, end result, I need 4 equivalent groups. So how many do I have to use?
4.
I have to use all 4. So if I run this to generate methane, I'm going to create 4 molecular orbitals. Okay, ta-da, there they are. These molecular orbitals are different from the atomic orbitals. Why are they different?
Because they've been averaged out.
Because one says molecular and one says atomic. Keep it simple. Okay, that's literally all I want. Okay, they are different. Okay, what do I want to name them?
From what they came from?
Pop! My son comes out of my wife's womb. What do I want to name him?
Sue.
It's a nice reference. Okay, we could name him Sue. Okay, if you don't get that reference, don't worry about it. Okay? Or Bob, or Sally, or Jerry. You could name him anything. Okay? We could name these orbitals that have now come into creation through our mental processes anything we want. Okay? But what we decided was that we want to name them with something that allows me to understand where they came from. Okay? So if you take the letters of my son's name, Corbin, and you rearrange them, you get my name and my wife's. No, you don't.
Oh, look, I was like, no.
But that's what we did here. Who are the parents of these new orbitals? The s orbital, the p orbital, the p orbital, and the p orbital. Which means the name of it becomes sp3. How about the name of the next one? It's identical to the first one, which means sp3. The next one? They're all sp3. So the hybridization comes from recognizing that I have 4 equivalent groups of electrons. Okay? It becomes a little bit different when we scale out to double and triple bonds. But one of the biggest misconceptions that I want to kind of address when we deal with this is that I get a lot of students telling me, well, my teacher said that the sp3 come from single bonds. I did spell that right. No. Nonsense. Utterly false. Your teacher told you that because it is easier to tell you with the examples that they chose that single bonds ties to sp3. That is not true. It's the number of electron groups. That's what dictates your hybridization. Okay? So for a quick example, because you're like, that is nonsense, my teacher was awesome. I'm not saying they weren't awesome. Just for the record, that is recorded. Did not say your teacher was not awesome. I think I did that right. Are those single bonds?
Yes.
Yes. What's the hybridization? sp2. Why? There's only 3 groups of electrons. 3 groups of electrons means I'm going to use the s and 2 p's. sp2. Why is it sp3? 1 group bond, 2 groups bond, 3 groups bond, 4th group non-bonding pair, sp3. So not only do you need to track with the common bonding patterns, you also need to track with what are those hybridizations. Because those hybridizations are going to help you predict things about reactivity if you have them at the tip of your tongue. If you don't, you're going to have to use other techniques like memorization to figure out how those things are working. Kind of make sense? Yeah.
Why didn't they another?
Right. If you remember back in Gen Chem with hybridization, you may have heard of something sp3d or sp3d2. Those are fantastic. S, 3p, d would be 5 groups of electrons, which would be what shape? Trigonal bipyramidal. Why is that not on my list? I don't care about that shape. That hybridization does exist. It's completely irrelevant to OChem. Same thing with sp3d2. Okay? So we could go through and use this to help explain the molecular orbitals for an individual atom. Okay? So if I went through and wanted to look at the molecular orbitals for CO2, the first thing I would need to know is the Lewis structure. So we could follow through all of our rules, and I get this for an answer. What is the shape for CO2?
Should be linear.
So what's wrong with this Lewis structure?
Nothing.
There's nothing wrong with this Lewis structure. Okay? Because Lewis structure does not imply shape. What's wrong with me drawing this and saying this is CO2?
It's nothing.
That's not how the rest is.
What's wrong with me drawing this and saying that this is what a human looks like?
Because his head is in his groin.
I mean, some
We
books
could
like that.
use some fun descriptions. Okay? All the parts are there, but they're put in the wrong locations. Right? When we draw out a Lewis structure, we aren't trying to draw a Lewis structure anymore. What are we trying to draw? The most accurate representation of that molecule. Okay? So we have to be careful that when we go through and draw out our structures, we want to mimic that representation as best as possible. We know that this one is linear because it had two groups of electrons, which means linear. Two groups. One group, two groups. Okay? Two groups of electrons means how many hybrid orbitals? Two hybrid orbitals. So I'm going to draw two hybrid orbitals. What do I want to name those two hybrid orbitals? SP. Because I've created two molecular orbitals, I'm going to use two atomic orbitals. Can I destroy these p orbitals?
No.
No, which means
They're still there.
they are still there. There's those p orbitals chilling out there. Right? When I go through to try and describe what's happening with the molecular bonds, I could also do this now for the oxygen and set up the same system behind it. So this was our carbon. What happened with the oxygen? Let's go to my stupid little man. How many groups of electrons for the oxygen? 3, which means 2, 3, sp2, 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 and
P.
a leftover p orbital. When I go through to now look at the bond, okay, I only want to look at one of them. I meant to use an eraser, but that's fine. Okay? I want to look at what's happening at the connection between the carbon and the oxygen. Okay? Well, the carbon is contributing to this what orbital? This nice big heavy fat part right there. What is it contributing there? An sp orbital. What is the oxygen contributing to make that bond? An sp2. What the heck happened with the second bond? I've now showed an overlap of two orbitals to make one of those bonds. How do I get another bond? I can't use another sp because I know those are aimed the opposite direction. The sp2s here are aimed out to the angles, to the sides of that. How can I get more electrons there? They can't occupy the same space, which means I'm going to have to use a different system. What's that extra system? The carbon is going to contribute a remaining p orbital. What is the oxygen going to contribute? One of its remaining p orbitals. And we now have two sets of electrons occupying that space, which means I have a double bond. Are those bond overlaps the same? Okay. That becomes a much harder question. If we align and look at the picture for our carbon, there's an sp orbital. How is that coming about? Well, in sp, we're taking a sphere. Let's not draw it that way. And a dumbbell. You guys remember positives and negatives? Like you might have seen shaded and unshaded, or positives and negatives. Okay, when we looked at a dumbbell, a p orbital, we usually see a positive and a negative, right?
Yes.
Yeah? So that dumbbell is positive and negative. Does the s orbital have both positive and negative?
No.
In the same drawing? No, it's either positive or negative. Okay? Are you guys optimists?
No.
Okay. Damn. Okay, let's switch those around then. That was not the answer I was expecting. So that makes our s orbital a negative. Okay? What happens when I overlap a negative with a negative?
Becomes more negative.
It just becomes more negative. What happens when I overlap a negative with a positive?
Becomes less
Neutral.
It cancels out. What's the shape I'm drawing here?
More negative.
one side bonus.
One side is more negative because I've got negative contributing to negative. The other side is positive canceling out the negative. That's the shape of our sp hybrid. It's an overlap of those two orbitals. When I go through and look at the oxygen, the same thing happens except with different orbitals. And I'm going to get something along, whoa. Let's try it this way. If you knew what I was trying to draw, you would have understood my whoa. Okay? And what makes the bond?
That space in between.
The space in between here. Where what do we have? A negative and a negative. Those now overlapping mean electrons shared between, which means we now have a bond. Okay, well, what was the other bond contributing to this? Or sorry, the other orbitals. Our p orbitals. Where is the p orbital on the carbon? 90 degrees away. With its positive and negative. Where's the p orbital on the oxygen? 90 degrees away. With its positive and negative. Do you see an overlap of those orbitals? It was a nice vague question, so technically yes and no works for that.
Yes.
Okay, I saw a no first. When I said of those orbitals, when you're saying no, which orbitals are you referring to?
Well, the top p orbitals, but
You're saying the
there's
p.
literal, there's no overlay, but the electron will spread.
We'll get to that in a second.
Okay.
The p orbitals do not overlap.
Right.
Okay, so you're saying no overlap. If there's no overlap, there's no sharing of electrons, which means no bond. If you said yes to overlap, you were probably referring to the sp hybrid ones in the middle. Okay, and that's cool, as long as we got that down. Okay, this is the fun part with electrons. Okay, fun. Okay, electrons are nasty little, devious little buggers. They don't travel in straight linear paths. They can hop. Okay, they can't hop infinite distances. And so what do I mean by hop? Like if I hop from here to here, I occupy the space all the way between there, right? Electrons don't. Electrons hop by existing here. Close your eyes. I can't hop with you looking at me.
We want you to see your
Oh my gosh! Look at that, I moved. How did that happen? That's what an electron is doing. It does not exist in the space in between. But as long as that distance is close enough, it can hop. Guess what the distance is between those two p orbitals?
within that hop length.
That's the hoppable distance. Which means the electron can jump back and forth, which means there is a bond. And now I have two bonds. Okay? Little thing to watch out for on that, right? Because we said p orbitals are 90 degrees away from each other, yeah? Yeah? Okay, so if I'm drawing out this system right here, I want purple. P orbital, yeah? Okay, they can hop because when we look at it this way, what do you see? Overlap. You mean like overlap where I can form a bond? Yeah, there it is. There's the overlap, it does exist. Just because when I look at it this way, I can't see that overlap doesn't mean it's not there. Okay? But what could we say single bonds could do? They could rotate. Okay? So what if that single bond rotated? Do you see the overlap?
Yeah.
Careful, remember these are examples. In the p orbital, what's in the middle? Nothing. Is there overlap?
No.
There is no overlap. The overlap only happens when the p orbitals are in the exact same plane. That's when the electrons can jump, which means the instant I have the ability to have p orbitals align, what happens to the ability to rotate?
It goes away.
It goes away.
It goes away, because the instant I rotate it, I'm now saying, electrons, stop moving, you can't move. Right? Roughly equivalent to you if I said 45, right? Okay. For the next half an hour, you cannot move. No blinking, no breathing, nothing. You'd probably get a little stressed out. Okay? Same thing is happening to electrons. So as soon as we have the option to do it, it's now locked into place. The only way I can potentially rotate is if I provide some incentive. You get $1 million if you don't move for the next half hour. You don't. Don't quote me. That might have been recorded, but no, I'm not doing it. Okay? Same thing's happening with our electrons. We can rotate that p orbital if we provided an incentive. What's the incentive? A crap ton of energy to get it super excited. Once it's now super excited, it can rotate. Okay? So when we're looking at our bonding, this is what we get. Okay? Which brings in the next kind of layer to this. Okay? We get the overlap between p orbitals, and we get this blue overlap in here between our hybrid orbitals. Are those the same types of overlap? No. Are you the same person as me? No. How do we distinguish that?
You talk different, you act different.
How would we distinguish it? How would you tell someone that I am different from you? She said it, not me. Different names. Because we have different overlaps, we need different names. So we'll call the blue overlap Sally and the green overlap Bob. That doesn't match with how we did hybridization, so let's come up with a better way to do that. What orbitals are being used to overlap in the green case? P orbitals, and P begins with, didn't quite work out that way in my head. The Greek letter for P would be? Pi. What type of bond is that?
A pi bond.
That is a pi bond. I don't actually know if this is true, but hey, legit, it matches, so I won't use it. What orbitals did we use to make the blue overlap?
S.
Those are s orbitals? You go into my 130 class and draw this little goofy looking shape here and say that's an s orbital, they're going to be like, yeah?
No.
No, it's not an s. It's an sp? The oxygen was an sp? sp2. So when I have sp2 orbitals, I get the blue one, right? What was the red one? That's not sp2. So I get this type of overlap involves, these are sp and sp2, s-type orbitals. Is an sp2 orbital an s-type orbital? How do I know that? It says S. That's it. Is an sp orbital an s-type orbital? Yes, because it says S. Is an sp3 an s-type orbital? Because? Is an s orbital an s-type orbital? Yeah, that one should hopefully be the most obvious. It's literally an s orbital. Of course it's an s-type. The Greek letter for S. We now get the existence of those two bond types that we were talking about earlier in the semester, okay, when we're looking at Lewis structure. We don't have double bonds anymore. A double bond is not a double bond. A double bond is
A sigma and
a sigma bond and a pi. Okay, a triple bond would be a sigma and two pi bonds. Would I be able to put another pi bond in that same plane?
No.
No, it would have to be a p orbital located where?
Coming in and out of the screen.
90 degrees to this one. So like right here?
No.
No, it's in the same place the sigma is. So where is it? three-dimensional is coming in and out of the plane at you. Okay? This is where you could deal with dashes and wedges. You don't want to draw dashes and wedges on p orbitals. It's just not pretty. Okay? The textbook does attempt to do this, and because the textbook is a hell of a lot better of an artist than I am, they can pull that off. I can't. But this is hybridization theory. Hybridization theory gets us those hybrid orbitals. We then overlap those hybrid orbitals to create different types of bonds, sigma and pi. Okay? Which means single, double, and triple are irrelevant terms for the rest of the semester. Year. Use sigma and pi. Okay, so the next fun question, which bond is higher in energy?
The pi bond.
Why is the pi bond higher in energy? What orbitals are used to make a pi bond? P orbitals. What orbitals are used to make a sigma bond? SP or S type. Which is higher in energy, S or P? P. The pi bond is higher in energy than a sigma bond. Okay? It falls out of our atomic theory or our molecular theory. Kind of makes sense? We jammed a bunch of crap into that one slide, so we might have to skip a couple slides here. How are we feeling now with hybridization? A little better?
Yeah.
Okay, we'll still have to manipulate. You still have to look at structures to try and nail these things down. Just like looking at a Lewis structure and trying to draw out a compound, you should very quickly be able to identify hybridization. BH3. We draw out a Lewis structure. Hybridization is sp2. Okay? There's only 3 groups of electrons. Does anybody have someone screaming in the back of their head like, but?
No.
No octet. Yeah, I agree. There's no octet. Doesn't matter. There's no electrons. I can't satisfy the octet. Interesting feature, though. If it's sp2, what's left over?
P orbital.
A p orbital. What's in that p orbital?
Nothing.
Nothing. What could I put into that p orbital?
Electrons.
Electrons. I've now just predicted the reactivity of boron. Boron can accept 2 electrons from another molecule using hybridization theory. That's the beauty of this system. Okay? So we will constantly cycle back and reference these things. Okay? Those are going like, this is a lot. It is. Yeah, it is. Okay, it is. We just have to work with it. Okay, at this stage, we're building fundamentals. What will happen is we'll start applying these fundamentals to everything afterwards. Okay, that's where our end goal is. Okay, some interesting results of hybridization. If we were to draw out Lewis structures, do I have nice pictures? I don't have nice pictures. Okay, but you could draw out Lewis structures for these. Are you guys ready? I heard a kind of a yes. Yes. Okay.
We are ready.
3, 2, 1, draw the Lewis structures. For those of you wondering, yes, this is now a race. Those of you who are looking down, didn't matter. There's our 3 structures. Should you be able to draw them that fast?
Yes.
Little-ish. I knew the answers, so okay, kind of cheating. But you should be kind of on top of it that fast, recognizing those patterns behind it. So we've got these 3 structures. Okay? The interesting feature behind this, %S character. Well, what the frick does that mean? How much S character, and actually I don't even want to point at that carbon, is in this bond?
25%.
What are you talking about? We're talking about that carbon, the %S character of carbon with those bonds. Well, with 4 groups of electrons, the hybridization would be sp3.
25% as character. Oh.
It is 25% S. Because in the 4 orbitals that contributed to that molecular orbital, one of them was S. How about the next one? 33%, sp2. Last one?
50% SP.
That's cool, Mike. You can do math. What does that do for us?
It changes the way the electron will have.
What is the difference between an s orbital and a p orbital?
As the electron's closer.
Lower in energy. Why is it lower in energy? The electrons are held
Closer.
closer. So when I move from an sp3 to an sp, I'm increasingly becoming more and more s character, which means the carbon is doing what to its electrons?
Pulling them closer.
Pulling them in even tighter. Is there a word that describes the ability for an atom to attract bonding electrons to it?
Negativity.
Electronegativity. The sp carbon is
Effectively
more electronegative
Than any of those.
than any of the other ones. You're like, well, that's not a big deal, dude. I don't really care. Hydrogen versus chlorine. There's a difference in electronegativity there, right? Do you care about the difference in electronegativity here?
Yes.
Yeah, because that burns me. That's an acid. Guess what happens to the reactivity of the triple bond, or that hydrogen at the end now?
It becomes acidic.
It becomes acidic. Okay? So I can memorize that the alkyne hydrogen is more acidic than the others, or I apply hybridization theory and I don't have to memorize the fact. Okay? I fully expect you to memorize it because you haven't had time to process it enough. Okay? So, our orbital overlaps, we did just kind of address it. This is with a different molecule, though. We've got kind of our nicer picture in this case. So we've got the C2H4. You'll notice that the textbook took the structure and twisted it. Why did they twist it? Okay? Because if I was to draw that out, what is the shape of that carbon? What is its geometry? Trigonal planar, which means that structure could more easily be drawn like this. Which of these representations is better? My little goofy red one or the black one that's neatly drawn by the textbook?
They both do different things.
They do different things. Do you really want to draw wedges and dashes on every single structure you do?
No.
Okay, so those of you who said black, that's what you just said. I want to draw wedges and dashes on everything I do. No, you don't. You'll get sick of it very fast. When we draw out our structures, we try to draw them as simple as possible, which means we will draw things with solid lines representing the plane of the molecule. And if we can avoid it, we will avoid showing any wedges and dashes. Okay? So why on earth would the textbook go through and switch the view to this weird side view thing where they got to show all the wedges and dashes?
So they can demonstrate where the p orbitals are.
Where are the p orbitals making that pi bond? In the case of the one that's planar, the p orbitals are located
In and out of.
in and out of the plane of the paper. How easy is that to draw? That sucks. I wish I could draw it so they were in the plane of the paper. To do that, what do I need to do?
Wedges and dashes.
Take the molecule and turn it on its side. Now when I draw through, the p orbitals are in the plane of the paper, I can see them. That's why it's twisted. Okay? What does this mean to the compound with that pi overlap? We addressed this. Because I have pi overlap, what does that mean for this structure? Here's your hint.
It's not rotating.
Ah, no rotation. You had to think back, what were all the other hints you did? Yeah. There is no rotation now. We're locked into that alignment. Okay? The way we would see that is if we took that molecule And we now turned it out this direction. So depending on what you are trying to do or visualize, you may change your perspective. The drawing is this. Here's the p orbitals. Well, officially more like this. Okay? Where they're aligned so they can not overlap. Okay? If we change our view, now we can see the overlap. Only when we take and rotate things. Okay? The fun part with this, which of those rotational views are you expected to know? All of them. Every single one of them. Okay? That's one of the reasons why OChem becomes challenging, because you have to be able to manipulate these structures in 3 dimensions. Okay? So looking at these 2 structures up top, are those the same or different? Different. They're different. Okay? But if I had instead written out would those be the same or different? Those are the same. One of those is me. Ta-da! One of those is me. Is it still me?
Yeah.
Yes. Okay? What happens when we drop in the double bond?
Rotation stops.
Okay, the rotation stops. One of those is me, and one of those is me with a back cast on that prevents me from turning. Okay, or a neck brace. Okay, which, by the way, I've had to wear. And people usually find that hilarious when you have to wear one. And they take advantage of this exact same principle. Because what do? They see you walking down the hall, and you're like, yeah. Hey, Mike. Same thing is happening here. So what we have to be able to do is to recognize that and decide that they are different. And if they are different, we then have to call them different things. The different terms that we bring in at this stage is cis and trans. Cis, because they're on the same side. What's on the same side? That's a good question.
Yeah.
The 2 pieces that are biggest are on the same side. So in this case, these R groups are on the same side, which would mean this structure is cis. And the next one, these 2 groups are on opposite sides, which means that structure is trans. So now when we look at a structure, we should be able to decide, does it have this issue of cis-trans isomerism? Which really means look at it, is it cis? Then yes, it has cis-trans isomerism. Okay? If I look at it and I'm like, I don't know if it's cis or trans, then it doesn't. Okay? To be able to do that, we have to see what? Placement of what? What's the functional group R? That silence is telling. Don't tell me functional group. Something. Of atoms. I have to see the placement of 2 atoms. Where are those 2 atoms located?
Opposite side.
I'll accept opposite side for trans, but I wouldn't accept opposite side for here. I want to use a rule that allows me to distinguish both of these right out of the gate. Where do those 2 things have to be located? I might have heard somebody say it, across the double bond, on the different carbons of your double bond. Okay? So let's take a look at this last one. How many big groups do we have? Okay, so there's our double bond. What are our big groups? Right? Okay, so we're looking at that last one. There's the double bond. There's an R group. Yay, an R group. Where's the second one?
There isn't one.
There isn't. What does that mean?
There is no trans.
Not cis-trans isomers. Okay. Next one down. Where are your big groups? Mother F nuggets, how many are there? There's 4. 1, 2, 3, 4. Okay. I need to be able to distinguish those groups from each other. When we go back up to here, this is R versus H. Can I tell this from this?
Yeah.
Yes. Which one do I think is more important?
This that you're pointing at now.
The one I'm pointing at now? Cool, I agree with you. Which one is more important, this or this? Ah, I can't tell a difference. Do I have a second R? No, that one does not have cis trans. Okay. Next one.
You've got 3 different groups.
3 different groups. Can I tell a difference between these two?
Yes.
Which one do I want to say is more important?
The top one.
Okay, top one, R. Move to the other side. Well, there's only one big one, so I don't really care. Does this one have cis trans isomerism?
Yes.
Do I have 2 R groups?
Yes.
Are those 2 R groups located on different carbons of the pi bond? Yes, which means yes, I do have cis trans isomerism. The next question could be, is it cis or trans? And in this case, it is cis. It is only cis because we've decided that this was the larger R. At this point, I don't care. We have cis trans. This one is officially cis. How about the last one? Or the first one, depending on our perspective. That looks like 2 R groups, right? So does that fit our cis trans rule? Yes, you're shaking your head no. That's gutsy. You're saying no, it's not cis trans. Why are you saying no, it's not cis trans? It's a cyclic structure. What is that cyclic structure preventing? Rotation. I can't physically get this into the trans isomer. This doesn't have cis trans isomerism because there's another feature preventing any possible rotation. So that one is also a not. Yeah? Kinda? Kinda. Okay, I can accept kinda. Okay. Our atomic to molecular. This is looking at molecular orbital theory, or a really kind of, and I hate to use this word, but it's largely my fault that it is this word, so it's okay, a dumbed down version of the linear combination of atomic orbitals. When we talked about our p orbitals, right, we said there was a positive and a negative. What is that positive and negative referring to? The phase of a wave. What the hell is a phase? Whether it's above the line or below the line. If you got a better definition, you can talk to me outside of class. This little part of the line is above the line, so it's positive. This one is below the line, so it's negative. Why are we talking about waves?
Because electrons demonstrate
Because electrons are waves and particles. Okay, that whole hopping thing, ta-da! There it is. This is why they do it. This is stupid wave stuff. So you got to deal with phases. Okay? The reason why we bring this up is what's happening is we're bringing these 2 orbitals near each other. We're taking 2 orbitals to what type of orbitals? Begins with an A. Atomic orbitals. Okay? And I'm going to take these 2 orbitals and I'm going to bring them near each other. Where am I bringing them near each other on? What is that thing that I drew between those? A plane would imply 3 dimensions, so I'm going to say no. Seriously?
a line.
A line. Okay. And I am bringing them close enough to each other that what can happen?
They overlap.
They can overlap or
Interfere.
combine. So you may have heard reference to in your Gen Chem class the Lakow-Mott theory, linear combination of atomic orbitals, molecular orbital theory. That's what it's coming from. You literally take 2 spheres and I bring them near each other and see what happens. That's it. Yes. Everything we're doing, that's all it is. Okay? So here's where it gets a little bit wonky on us. Let's see. Do I have a prettier picture? No, I don't have a prettier picture. But this is a little bit cleaner looking. Okay, so I'm going to take these two s orbitals and I'm going to bring them near each other. S, S. I bring them near each other. Well, before I even bring them near each other, I have to acknowledge something. That something I have to acknowledge is that these orbitals are describing electron motion. An electron moves in waves, which means it could be positive or negative. So when I bring these two orbitals near each other, there's a chance that they are positive, both positive. There's a chance they're both negative, and there's a chance that one's positive, one's negative. If we look at all those possible combinations, there's really only two outcomes. There's the outcome where they are in phase with each other. Okay? So if we drew that, they're now overlapping like this. There's our nucleus in between, right? And we have this overlap. And I'm going to wish I could cut and paste better. There's our overlap in between. If they were in the same phase, say positive, positive, what happens in that overlap? Remember, same phase. This is a wave.
They get bigger.
If they're both positive, they get bigger. I get more intensity there. Remember, the shape is supposed to be an intensity. So if they're overlapping, there's a larger intensity. So that representation would be like, there's my nuclei, more intensity. I've got a larger space in between them, which sounds an awful lot like I know. Who would come up with these things? Like I have more electrons between atoms. Kind of sounds like like a bond. That's a good word, right? This is a bonding interaction. Would I predict that bonding interaction to be lower or higher in energy than the atomic orbitals? Do we exist? Are we just a collection of atoms, or are we a collection of molecules?
Molecules.
A collection of molecules. If molecules were higher in energy than the atoms, would they ever form bonds?
No.
No. Where are bonding orbitals?
Lower.
Lower in energy than our atomic orbitals. It's the only thing that makes physical sense. Okay? That was if they were both positive or both negative. Because I'm an optimist, screw y'all, I'm going to say they're positives. Okay? There's another option. They could have come in where it was positive and negative. What would happen to the space in between now? Now it gets canceled. What does it look like? A space in between. This space in between, people have written songs about, right? Is called a node. Okay, it's where the electrons don't exist. We now have a node. Okay? Is that a bond?
No.
No. Is it not a bond?
No.
Because not a bond means they were never there. Are they actually interacting?
Yes.
Yes. So that's not a bond. For those of you like, well, what the? Yeah, this is the problem. Because not a bond means they aren't interacting. This is a legitimate interaction that could have come out of this. So it's not a bond. What is it? I need a new word. This is an anti-bond. The way to think about this is a bond is they're forming like a bond. Like everyone's okay with that. An anti-bond is actively not bonding. Not bonding is just, yeah, I'm not bonding. Anti-bonding, I am actively not going to interact with you. I'm going to do everything I can to not talk to you. That's anti-bonding. Okay? Molecular orbitals are now the description in between. We have now linearly combined these to see how they would form. In the process, we generate two new pictures. What about this third one? That was just some non-stuff stuff so you could see what it looks like, so we could ignore that. Okay? There's two new pictures. These describe the bonding in a molecule. I now have molecular orbitals. I got the molecular orbitals by linearly combining atomic orbitals. Molecular orbital theory. Lac-Mott. That's where it's coming from. Okay? So if I now wanted to describe all of this in detail, because, you know, it's not like we're out of time or anything, we could describe the type of overlap. This is a direct overlap, which matches the, I completely agree, sigma bond that we talked about earlier. Okay? The top one is still a direct overlap. It's a direct overlap that resulted in not interacting. So it is still a sigma type interaction. But I need to signify that it's actively not interacting. Sigma star. Okay? Every kind of orbital that you can imagine, hybrid, unhybridized, p, sigma, can do this. When we move into more complex structures, we tend to ignore most of it and only look at the p orbitals. Right? And we only look at the p orbitals that are overlapping through pi systems. We tend to ignore the sigma ones. Why would we ignore sigma in deference to the pi? Pi is higher in energy. Why would I care about the higher energy orbitals? What's going to be more likely to react? The highest energy. When we look at Lewis structure, which electrons do we look at? The valence. We don't look at the core. Why? Higher in energy. Everything we're focusing on is those highest energy. This is the fundamentals that builds it. We get nodes, we get the stars. Depending on what orbitals we get, we could even get pi bonding and pi anti-bonding. That's pretty much the rest of Chapter 3. I don't know how much more I'll actually talk about Chapter 3 on Monday. Okay, but we'll see what happens with timing, because I think we covered the bare bones basics of it, and I really kind of want to keep moving. Okay, we are officially